Greetings, young mathematicians. I would now give a short lecture on finite groups and group tables. But before I start, let me first give some clarifications on the misconceptions that I have observed when I went over your learning tasks. I noticed that you have not fully understood the observations about proofs in the first pages of our textbook. So I suggest you read those pages again and try to fully understand the statements, the observations in the construction of proofs. Okay? What I would like to highlight here is that in constructing proofs, a case wherein the statement is true does not prove the statement, nor does it disprove the theorem. Meaning, a an example wherein the statement holds true is inconclusive. But however, an example wherein the statement is found not true or false, or the statement does not hold, disproves the statement. So that is the difference between the two. Again, an example wherein the statement holds is inconclusive, but an example where the statement does not hold disproves the theorem. We call that a counterexample. Let me show you a particular illustration for that observation. Here we have the operation asterisk defined in the set of positive integers z by the statement A operation B is A to the B. Okay. Actually, this statement holds true if we take the numbers 1, 2, and 3, just like what you did in your learning task. So if we can see, so if we have the quantity 1, operation 2, operated to 3, would be, by the definition of our operation, 1 operation 2 will be 1 squared. I'm sorry. Erase this first. That would be 1 squared operation 3. But then 1 squared is just 1. So this will be equal to 1 operation 3. Then apply the definition again of the operation. 1 operation 3 will just be 1 cube, which is equal to 1. On the other hand, if we regroup, taking 1 operation, the quantity 2, operation 3, this will be equal to, so we take first 2 operation 3, so we just carry over 1 operation 2 operation 3 will become 2 cube. So that is 2 cube, giving us 1 operation 2 cube is 8. So 1 operation 8. And again, by the definition of the operation, this can be written as 1 to the 8th. But 1 to the 8th is just equal to 1. So we see that both expressions lead to the answer 1, meaning the quantity 1 operation 2 operated to 3 is equal to 1 operation 2, 1 operation the quantity 2 operation 3. But again, as I have said, this is a case wherein the statement holds true, and as I have said, this cannot actually say, or this cannot be the basis for saying that the operation is associative, when in fact it could be proven actually that the operation is not associative. That is, let's say for example, if we take the numbers, let's say 2 or the quantity 2 operation 1 operated to, let's just say 2. So this will give us 2 to the 1 by the definition of our operation. 2 operation 1 is 2 to the 1 operation 2. But 2 to the 1 is just 2. So 2 operation 2. But 2 operation 2 by definition is just 2 squared, will give us 4. But if we change the grouping and write that as 2 operation the quantity 1 operation 2, that will give us 2 operation 1 squared. But 1 squared is 1. So this will be equal to 2 operation 1. But 2 operation 1 by definition of the operation is 2 to the 1, which is equal to 2. Hence, we see that the quantity 2 operation 1 operated 2 is not actually equal to 2 operation the quantity 1 operation 2. So we see a case wherein the operation is not associative. In other words, the operation is not associative for all positive integers. The associativity does not hold for all positive integers, just like what is illustrated here. So from this example, we can conclude. So we say, therefore, the operation asterisk is not associative. Associative. So we can get a conclusion from an example wherein the statement does not hold. We actually call this a counter example. So a counter example disproves a statement. But an example, as I've said earlier, an example where the statement holds true does not actually prove anything. Okay, but if we want to prove a statement, since we see that it is obviously true for any element of the set where it was defined, just like, for example, we defined the operation asterisk in the set of integers by A operation B is the additive inverse of A added to the additive inverse of B. So clearly, this operation is associative. But in proving associativity or for proving any statement for that matter, we cannot use particular example. Instead, the terms that we have to use should be arbitrary representations of any element in the set wherein the operation was defined. Meaning, we cannot make use of particular elements just like 1, 2, 3, and so on. So, the proof should be one wherein arbitrary elements of the set are used. So, let's say, take A, B, and C be elements of the set of integers wherein the operation was defined. So again, A, B, and C may represent any of the elements in the set. So if we take the quantity A, operation B, operated to C, by definition, A, operation B, from this definition here, would be, this would therefore be the quantity negative A plus the negative of B. Okay, so that is A operation B. The result, this result, would have to be operated to C later. So, operation C. But then, this quantity operated to C will just be the negative of negative A, sorry, negative of negative A plus the negative of B. Okay, the negative of this whole quantity plus the negative of C. Sorry. Negative of C. Okay. But if we simplify this, we can have this written as the negative of A, okay, minus the negative of B plus the negative of C. Okay, which may then be written as negative of negative A plus B plus the negative of C. Okay, so this may then be written as A plus B plus the negative of C. Okay, so it seems like this is far from the expression resulting when we regroup the three. Let us check. So this would be the quantity A operation B operation C, whereas if we have A operated to the quantity B operation C, we would have A operation negative B plus negative C. Okay, so this is negative B. But that would be the negative of A plus the negative of that whole quantity. Negative B plus negative C, which would give us negative A plus the negative of negative B is B, then the negative of negative C is C, so plus C. So this gives negative A plus B plus C, whereas the other one is A plus B plus negative of C or minus C. Meaning, there would be instances, there would be integers wherein these two expressions, the quantity A operation B operated to C, will not be equal to the quantity to A operation the quantity B operation C. So if this happens, again, this does not prove anything because we have not found that the two expressions would lead to the same expression, or to the two expressions are not equal. So in this case, we would have to show again a counter example. We show a counter example, just like what we did in our first example. So take for example, let's say 2 operation 3 operated to 4 would be equal to negative 2 plus negative 3 operated to 4. So this would be equal to negative 5 operation 4, which gives negative of negative 5 plus negative 4, which should give 5 minus 4, or simply 1. 5 minus 4, or that can just be written as 1. Whereas, if we take the expression where the grouping is not the same as that, but the order is the same, so that is 2 operation the quantity 2 3 I mean 3 operation 4, this would be 2 operation quantity negative 3 plus negative of 4. So this will give us 2 operation. This is negative 7. Or that will be negative 2 by definition plus the negative of negative 7. But this will just be negative 2 plus 7, or that will give us 5. So we see that the two expressions are not equal. So again, this is a counter example showing that the operation, so you can have this the conclusion, therefore the operation is not associative. Okay, again, if we recall, this happened because we were not able to prove that the operation was associative. And if we would try to recall how we attempted to make the proof, again, in making proofs, we cannot make use of particular elements. Instead, we use symbols representing any or arbitrary element of the set. If it did so happen that this expression, this one, if it was the case that we found that this expression can be transformed or can be written so that it will be equal to this, meaning this expression will be equal to this one. So if that should have happened, then we could have proven that the operation was, or the operation is associative. Okay? Only if it did happen that these two expressions were the same. So this would be our proof. But then we failed to do so. So we have shown a counter example. Okay, so I hope I have made everything clear on that matter. Let me now proceed to what we really are to discuss in this instructional video. So we have the concept of finite groups and group tables. So far, in most of our examples, groups or the sets wherein we have defined a binary operation and proven that they are groups are all infinite. Just like, for example, addition on R, or the set of real numbers under addition is actually a group. The set of integers under addition is also a group. The set of non-zero real numbers under ordinary multiplication actually is also a group. So far those examples have taken infinite sets. But the concept of groups is not actually limited to infinite sets. It can also be applied to finite sets. So that is what we are to discuss today. So when we say a finite group, it is a group wherein the set where the operation was defined is actually finite. So let us try to verify what would be, if there are finite groups, what would be the least number of elements? Okay, so what will be the least number of elements that can be contained in a set? So if we would recall the definition of a group, again, it should satisfy 3 axioms. But first, it should have a binary operation, meaning the operation should be closed and well defined in the set. Okay, then it should satisfy the 3 axioms. First, the axiom of associativity. That is, the operation should be associative in the set. The second is the existence of an identity element. So there should be an identity element. Therefore, it is impossible for a null set to be a group. Why? Because a null set does not contain anything. In other words, it would not contain an identity element, meaning this set cannot be a group. Cannot be a group. So there is no group with no elements. Why? Again, because of the axiom of the existence of an identity element. Okay? So the cardinality cannot be 0. So what is there a group with just one element? So if there is just one element, by that axiom, the existence of the identity element, such element must be the identity. So let us try to construct a group table with that condition. So if there is an operation here, so we have here an operation table, the operation asterisk, apply to just one element, meaning that element should be the identity. And since this is the identity, any element operated to this would go back as the same element, meaning E, operation E, by the definition of the identity element should be E, meaning the element here, E, operation E, should be E. In which case, all results are in the set. So again, we are dealing with the set, let's say S, with just one element, say E. And then the elements, the results in this table are, actually is, because it is just one, is in the set S. Okay? And no matter how we group this, no matter how we group operation E, the result will just be the same because E operation E is E and the operation E is E. There is only one result. So no matter how we group this, the result will be the same, meaning the operation described in this table is actually associative. So the associativity axiom is satisfied by this operation table. Also, we see that there is an element operated to E blank, so that the result is E. And what is that? By the table, it is E. E operation E would give E, which is the identity element, meaning E inverse, or the inverse of E, is just itself. Meaning, there is just one element in the set, meaning we just have to find an inverse for that element, and we found that its inverse exists, which is E, which is also in the same set. In other words, all the axioms required for a binary structure to be a group are satisfied by this set E with the operation, the set S with the element E with this operation table. So this operation table can now be called a group table. Then this is a finite group. It's set S, the singleton, set S with only the identity element as its content, together with this operation defined by this table. Meaning, there is a table with one element. Okay? So, therefore, we can say that the least number of elements for a table can be 1. Now, let us examine. Actually, any group with just one element will just be isomorphic to this. Like, for example, if we consider addition to the set containing only 0, 0 plus 0 is 0. So we have the same group table. If we take the operation multiplication applied to the set containing only 1, since 1 times 1 is 1, so the result would again be the same set. So this is a group, but all three are just of the same form, meaning they are just isomorphic. In other words, they are just they represent the same binary structure. Only one group. Okay, they can be considered as just one group. Now, let us proceed to our investigation whether or not it can be possible that there are two elements in a group. So, consider again the set S with two elements. If there are two elements, by the second axiom, the existence of identity, there should be the identity element, meaning one of the two elements must be the identity element. Let us call it E. And there is another element, let us just call it A, other than the identity element. Now, if such set constitute a group structure, so let us again denote the operation by asterisk. The elements are E and A, E and A. Since E is the identity element, meaning E operation E must be E, and E operation A must be A by definition of E. In the similar manner, A operation E must also be A. Now, in this operation table, we see that there is just one spot left, and by the third axiom that each element must have an inverse, meaning there should be something operated to A so that the result is E, meaning E should be found in the row that contains A. Okay, E, because A operation something should be E, so E must be found in this row, but there is only one spot left. And E, since there should also be something operated to A, so that the result is E, meaning something operated to A should be E, meaning E should also be in the column containing the element A. Therefore, E should be present in each row and E should be present in each column. But again, there is just one spot left, so that would be the spot for E. Okay, so in this case, the inverse for A is itself. Okay, the inverse of E is E, and the inverse of A is itself. Okay, we cannot find any other arrangement so that this would constitute a group, because if we put A here, there would be no E in this row and no E in this column, and that would violate the third axiom for a group structure. There can be no other arrangement other than this. This is the only group table or operation table that can satisfy a group structure. Okay? Any other group table that has two elements will just be isomorphic to this. Like for example, the group Z2, actually Z2, with elements 0 and 1, 0 and 1, under addition modulo 2. This actually is a group structure. 0 plus 0 is 0. 0 plus 1 is 1 in addition modulo 2. 1 plus 0 is 1. And 1 plus 1 is actually 2 in ordinary addition, but we are in modulo 2. So 2 divided by 2 is 1, remainder 0. So the answer here would be 0. And that will just be isomorphic to this. We only change E to 0 and A to 1. Okay, so any group with 2 elements would just be isomorphic to Z2 under addition modulo 2. Next. Meaning, basically, there is just one group with 2 elements. Such group would be isomorphic to Z2 under addition modulo 2. Next. Is it possible for a group to have 3 elements? Let us check. So, consider the set S with 3 elements. So, one of which should be the identity. The other 2 elements, let us say A and B. Okay, let us try to draw or to construct an operation table that describes or that can be considered as an operation for a group structure. So, let's say here, a table for asterisk operated to the elements E, A, and B. E, A, and B. So, E operation E should be E by definition of E. So, this would also be A and this should be B. A operation E should be A. B operation E should be B by definition. Okay. Now, A must have an inverse. In other words, E should be found somewhere here. Okay, if we put E here, E. Now, this spot, what can be put in this spot? Now, recall from the properties of a group that the equation A operation X equals B must always have a solution. Meaning, something should be operated to B. Something must be operated to B. So, A, rather. Something must be operated to A so that its result is B. In other words, B should be found in the row containing A. There should be B somewhere here. Okay? But there is only one spot, so it should be B. So, if just say we put B there, take note that there would only be one spot left for this column, and such spot cannot be taken by any other element but E. See that? Why? Because B must have an inverse, meaning E should be a result for under the column containing B. In which case, there would be no spot, no space for A. In other words, there would be no solution for the equation Y operation B equals A. Y will not exist if this is the case because A cannot be found under or in the column under B. In other words, this cannot be B. This cannot be B. This cannot be E. So we would have to go back to that situation, or to that condition here, that this here cannot be E. So there could be no other possibility but here. Okay, so this should be E. And by this argument that B should be found in this row, So B should be here. And again, all three elements should be found in this column. So there is no other possibility but E in this place. And again, A would be the only possibility for this spot here. And we cannot rearrange this. There is no other arrangement so that this operation would be a binary operation that describes a group structure. Meaning, there can only be one group structure with three elements. Any group structure with three elements must be isomorphic to this group structure. Okay, take for example Z3 with elements 0, 1, and 2 under addition modulo 3. Meaning we consider only remainders when the number is divided by 3. So if we construct the table for addition modulo 3 for elements 0, 1, and 2, 0, 1, 2. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 2 is 2. 1 plus 0 is 1. 2 plus 0 is 2. 1 plus 1 is 2. Divided by 3 is 0, remainder 2. So this would still be 2. 1 plus 2 is 3. 3 divided by 3 is 1, remainder 0. So this would be 0 here. Then 2 plus 1 is 3, which would yield again a remainder 0. 2 plus 2 is 4. So the remainder would be 1 when it's divided by 3. Okay, so you see that all results are found in this set. And since addition is associative, and there is a 0 in each row, there is a 0 in each column, meaning this is an operation that describes a group structure. If we would try to compare it with the group that we have derived, they are just actually the same, basically. Only the names are changed. See, E is changed to 0, A is changed to 1, B is changed to 2. The same is true for the other rows. Okay, so these are basically the same. In other words, as I've said, there can only be one group with 3 elements. All groups with 3 elements, therefore, are isomorphic to Z3 under addition modulo 3. Okay. Let us proceed further to a set with one more element. So, consider a set with 4 elements. Actually, that is your activity number 2. You are to construct a group table for a set of 4 elements. Okay, just for the sake of discussion, let us answer that activity in this instructional video. Sorry. Let's erase all of this. First, define a set. Again, let us define a set S with elements E and the identity and other 3 elements. Let's say A, B, and C. Then try to construct an operation using a table. So an operation table defined in the set. So we have the elements E, A, B, and C. A, B, and C. Now, by definition of E, again, this should be, the result here should be E, the result here should be A, the result here should be B, here is C, the result here should be A, here it should be B, here it should be C. Okay, next. From the axiom of existence of inverse, A must have an inverse, meaning something should be operated to A so that the result is E. So there should be E here. So let us just say E is here. E. There are two spots left and two elements left, B and C. We cannot put B here, otherwise not all four can be found in this column. Okay? As I have said in our earlier argument, all elements should be found in each row and all elements should be found in each column by virtue of this, that there should always be solutions to y and x in this linear equations. So all elements should be found in each row, all elements should be found in each column. So if we put B here, there would only be two spots left for three elements, E, A, and C. So it cannot be. Therefore, we cannot put B here. Meaning, there can only be one possibility, and that should be put C here. And that would leave this spot for B. Okay, and then, for this column, it already has A and E. So we cannot put B here, otherwise this row cannot contain all elements. So this should be C. That would leave B for this spot, for this space. Next here, for this space, we can either put A or E. If we put E, then this would leave A for this place, and that would also leave A here and E here. But if we put A here, let's try to do that possibility. So E, A, B, C, A, B, C, E, B, C. So this is C. So we could have written A here, A, and that would leave, no, this is not this, CB. CB. If we put A here, that would leave the space for E. So this should be B. This would be E. And this would be A. Okay? Still, all rows contain all four elements. Each column also contains all four elements. Okay. In checking the associativity of the operation, actually, we would have to resort to checking all ordered triples. And that would be quite tedious. So, in this case, we will just be satisfied by satisfying the condition that all four or all the elements are in each row and each column. Okay, for now. So we have found two group table, or operation tables that can or that may describe a group structure. Let's do another one. here is E, A, B, C, A, B, C. If we recall, we have started this by assuming that E is here. Suppose E was not here. Okay, suppose E was here. So if E was here, these two spots would be for A and C. C cannot be here, so C should be here. And this would be left for B. Okay, and then, in which case, this would be the space for no other than but E. Because if we put B here, there will be two B's in this row. So this should be E. Therefore, this should be B. So in this case, we cannot put C here. So C must be here. And A would be here. And next, we have this would be for A only. A. And this would be for E. Okay, so far, we have found 3 possible operation tables that may constitute a group structure, may describe a group structure. Actually, we can still find more. Okay, but to make the long story short, it can be proven or it can be shown that above the 3, there are only 2 distinct binary operations. These 2 actually are the same. The second, okay, let us number this. This was the first group table or operation table that I have constructed. This is table number 2 and this is table number 3. It can be shown that one is different from the other 2. Table 1 is different from the other 2. These 2 remaining or 2 last tables actually are isomorphic or basically the same. If you can find some more, it can be proven again that it would be the same as these 2 here. Okay, so you may continue with this analysis. So let us show that these 2 are different. If we would try to analyze or investigate in table 1, see in table 1, E squared or E operation E is E, A squared, sorry, A squared in table 1 is also E. See that? A operation A is E. B squared is also E. And lastly, C squared is E. Okay, whereas in table 2, E squared is E. A squared, what is A squared? A operation A is also E. Meaning, the inverse of A is itself in table 2. But B squared, what is B operation B? It is A. And B cubed, that is B squared B. Since B squared is A, so I'll have just A operation B. A operation B is E, or rather C. Am I right? Let's move this down. B squared is here is E. A, B, C is E, A, B, C. B squared is A. Then B cubed, that is A, B, C. Then B to the fourth, that is B cubed operated with B, another B. So C operation B is E. Therefore, B to the fifth will just be B. Therefore, if we would try to enumerate all powers of B in this table here, let us symbolize that by B bar, just for notation purposes. B bar is the set containing all powers of B. So of course it has B, or B to the first. Then B squared is A. Then B cubed is C. Then B to the fourth is E. B to the 0 actually is E, because B, the inverse of B is the inverse of B in this table is C. So B to the negative 1 therefore is C. B operation C is E. So all elements in the set are powers of B. Let us now examine for the element C. Let us enumerate all powers of C, integral powers of C. So C squared in this table C squared is A. Is A. Then C cube. C cube is A operation C. A operation C is B. C to the fourth. C to the fourth is B operation C. B operation C is A. Meaning, all four elements are powers of C. So if we write the set, let's say C bar as the set containing all powers of C. So C bar would actually contain C, and C squared we have A, C cubed is B, C to the fourth is E. That would mean C to the fifth will go back to C. So we see that in the first table, each element only has, or for element A, there is only one power, which is itself. A has two powers, A itself and E. The same is true as B. And we can see that the inverse of each element is itself in the first table. Whereas, in the second table, it is only A and E who possess such characteristic that their inverse are themselves. So we see that the inverse of E is E, the inverse of A is A. But that is not true for the other two elements. We see here that the inverse of B inverse actually is C. And C inverse is B. So we see that these two tables are not the same, basically the same, because their elements do not possess the same characteristics. Okay, so we see that this table here is not isomorphic to this. But if we would try to investigate the table we obtained in our third attempt, table 3. Let us try to investigate table 3. So again, powers of E will just be itself A squared, A operation A is C, A cube, that is C operation A, C operation A is E. Right? A, B, C. C. A squared is C, A cube, C operation A is B, not E. This is B. Then A to the fourth is B operation A, E. So the powers of A is the set itself. It contains all 4 elements: A, C, B, and E. For B, B squared is C. B cube, C operation B, A. And B to the fourth that is A operation B, E. So also the powers of B are all elements in the set, namely B, then we have C, then we have A, and E. For C squared actually is just E. So C cube will just be C. C to the fourth is E. So the only powers of C are E and itself. In other words, this structure is more or less, basically, actually, they are the same as this one. Only that E is represented by E here. A is represented by C. Then B and C are represented by A and B in this table. So that is why this table and this represent the same binary operation. Okay? Actually, there are special names for these groups. The group defined by this table actually is what we call the Vier group, or simply the V group. The V group. Characterized by the symmetric arrangement in the table. So you see that in the V group, the major diagonal consists entirely of E, and then each element is just a reflection of itself with respect to the main diagonal. So a reflection of A is A, then B, C, and so on. Okay, these two actually are isomorphic to the group Z4 that is the set 0, 1, 2, and 3 under addition modulo 4. That is, if we construct that one, 0, 1, 2, 3, 0, 1, 2, 3. So this is 0, 1, 2, 3, 1, 2, 3. Plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 0. 2 plus 1 is 3. 2 plus 2 is 0. 2 plus 3 is 1. 3 plus 1 is 0. 3 plus 2 is 1. And then 3 plus 3 is 2. So here you see that only 2 is the inverse of itself. Then for 1 and 3, their powers are all elements in the set. So here in this table, A stands for the element 2, whereas B and C for 1 and 3. But for this table, the other table, in this table, C plays the role of 2, and A and B play the roles of 1 and 3 for C4, Z4 under addition modulo 4. Okay? For finite sets containing more elements, the investigation actually is still open for more conclusions and properties that can be discovered. So I encourage you to continue with the investigation for larger finite groups. So we'll stop our investigation for finite groups of order 4 or 4 elements. Okay, so continue with your own investigation for larger finite groups. That ends this lesson, and I hope you are now ready to make or to work on your learning task. Thank you for your attention, and you may want to hit the subscribe button and the notification symbol for you to be notified whenever I upload more abstract algebra videos. Okay, thank you and good day.